Okay, chemistry time. This is going to be part 2 of yesterday's video, and this one is going to be called, we did covalent bonding, the concepts of covalent bonding yesterday. We're going to talk today about acid and base naming. I'm going to put semicolon, covalent naming, semicolon, polarity. Let's do this in reverse order. As I'm writing it, I spelled polarity wrong. There, I kind of fixed it. I'm going to restart that word, polarity. Let's put bond polarity. We're going to do them in reverse order as I was writing them. I decided I wanted to do it that way, mostly because really the first two, acid and base naming, covalent naming, are things that you do. And the polarity is something that we kind of just have to talk about. I can espouse the concepts to you, and then you can, you're really going to have to figure them out conceptually on your own. But that's something that we do very frequently. So let's look at polarity first of all. What does it mean for something to be polar? What's the word polar mean? No. Close. Usually, well, I wouldn't say usually, but in the context of science, we usually express poles as positive and negative. But polarity is the property of having poles. This just means that something has poles. And what do I mean by poles? I mean two relatively, what we usually consider opposite, but two disparate facies almost, having poles. The Earth, when we talk about a polar bear, that is a bear, not that has poles, although you could say the bear has a heads and a tails, which is kind of a funny way to talk about this. But the polar bear is a bear that lives near the pole, the North Pole. So Earth has a north and a south pole. Are those things opposite? Well, not in climate. Well, I shouldn't have said that. They have similar climates, and they're both cold, but they do directly differ in which one's hot and which one's cold at any given time. Not the one's hot, but which one's relatively warm. For instance, the South Pole right now, it just began summer. The North Pole, it just began winter. But this planet has poles. A magnet has a north and a south pole. We could say that a wire, an electrical wire with a battery attached to it, has a negative and a positive pole. For instance, these are all things that have poles. You could, if you were being pedantic, which is one of my main personality attributes, you could say that the sides of a coin are poles. They're part of the same object, but they're two opposite faces of it. You have a pole. You have a head and a tail. We could call it a tail. Feet, you could say your feet are a pole. But polarity is the property of something having these kind of opposite ends. And so when we talk about bond polarity, we mean that between any two atoms, there is some degree of polarity. We usually express it like this. If we have two hydrogen atoms bonded with a single bond, right? Let's show this another way, the same kind of way we did show yesterday. They're each sharing one of their electrons, which means they're sharing two electrons, which means they are satisfied. Why is hydrogen satisfied with 2? Well, it's just back to the octet rule. Hydrogen is satisfied with 2, where most other atoms are satisfied with 8. Which of these atoms are the electrons more attracted to? When I mean atoms, I mean which of the nuclei are the electrons more attracted to? It's a trick question. They're not attracted more to either of them. And so this is said to be a nonpolar bond. A nonpolar bond. They're shared, the electrons are shared equally. There's a mathematical way to do this that we're going to do in a second, but I want to give you an example of a polar bond first. Now let's look at this one. This is a very common substance. What is this?
Water.
Yeah, I'll show it another way. Both of those are different iterations or different expressions of water. And this, now think about this. You're an electron. What attracts you? What is your charge? Those are different questions. What is your charge? If you're an electron. Negative. What are you attracted to? Positive. Are you more attracted to hydrogen with 1 proton or oxygen with 8 protons and some number of neutrons? oxygen. You're more attracted to the oxygen. Just like if you're I'm trying to think of what makes high schoolers attractive to other high schoolers. If you have lots of Gucci paraphernalia, you're more attractive to people who like Gucci paraphernalia. You know? Because electrons are attracted to positive, and so things that have more positive are more attractive to them. So the electrons, because they're more attracted to the oxygen, spend more time with the oxygen, giving it a, we use this symbol, this lowercase delta, to mean it has a net charge, or a net partial charge. This is the lowercase delta. Lowercase delta. What's the capital delta look like, by the way? Remember from physical science? No. No, that's gamma. Delta is a triangle. But the lowercase one looks like this, and this means partial charge. Meaning it has some charge, but maybe not necessarily as much as a whole electron or a whole proton. So which end ends up being negative? That's my question now. I think about it this way. Which end is more attractive to the electrons? Because where the electrons go, that's going to be more negative. So which end is more attractive to the electrons? The oxygen end. So this is a partial negative, and because of that, this must be a partial positive. And it's the same thing with this drawing. Oops, I did it kind of backwards, but just pretend like I didn't do it kind of backwards. And you can even see that here. The unbonded electrons hang out with the oxygen. And this is a polar bond. This is a polar bond. Shared, they are still shared. It's still a covalent bond, but now they're shared unequally. With our marriage analogy, this is fine. It works. People share different amounts of themselves with their partner, and that's fine. There's a polarity in marriage. Like I said yesterday, I like to do cooking, and so I do more of the cooking, and there's an unequal sharing of the cooking. But just because it's unequal doesn't mean it's bad. That's kind of an artifact of the 90s and early 2000s that we thought if everyone doesn't have the exact same thing, for instance, in education, that it was bad, that everyone needs the same stuff. But that's not true. We know now, even though I teach you about this, if you're going to be a truck driver, you might never encounter this again in your life. It's interesting maybe to you. And I truly believe that the thought processes you develop in learning about things like this help you learn other things. But this specific thing is probably not necessary for you at all if you're going to be a truck driver. But I don't know you, so you might need it. Okay, so these are shared unequally, and so they have a partial positive or a partial negative end. And now here's the math that we do. We look at this chart that you can find on page 265, and you might even bookmark this because we use it a lot later in the year too. But this is a chart of electronegativities. Do you see the chart of electronegativities? We've encountered this before, right? I think we encountered this before. Electronegativity, this was in the periodic table at chapter 2, chapter 6. It's on page 265. Electronegativity is how badly this atom, when it's unbonded, wants another electron. It's an arbitrary scale. 0 is the lowest, 4 is the highest. Which thing is the most electronegative? Which atom, when it's unbonded, is the most electronegative? No. Fluorine. Fluorine is 3.98, which is the least electronegative. Francium, 0.7. It doesn't want another electron. It wants to get rid of the electron it has so badly. And fluorine, up in the top right corner, really, really wants one more so badly. And so what we do is we take the difference between those. Turn the page now. On page 266 it tells you the character. The bond, what we call bond character. If the difference between the electronegativities, we do this for, even if we have something like this, like the water, we just do it for one bond. Even though water has 2 bonds, we just do it for one bond at a time. So let's start with this one. What's the electronegativity? I'm going to do these in a different color. What's the electronegativity using that chart of hydrogen? What is it? 2.2. No units. It's arbitrary. It's a relative scale. What's the electronegativity of hydrogen? 2.2. What's 2.2 minus 2.2? 0. This is a bond. This is a minus sign. Don't get confused between those, but it shouldn't be that hard. Now, so is this, if it's 0, look in there, look at our little chart to tell us the answer. 0, what kind of bond is it? What's the bond character on this chart on 266? Nonpolar. Nonpolar. It is covalent because they're being shared and it's nonpolar. Now look at hydrogen and oxygen. What's hydrogen? We already know, 2.2. And oxygen? 3.4. I'm going to put it in front. 3.4 minus 2.2 equals, that should be pretty simple math, 1.2. And that falls in the range of 0.4 to 1.7, which is polar covalent. The one underneath that says mostly covalent, to me that means nonpolar. There's a range of kind of, it's not as easy as just nonpolar or polar. There's kind of a gray area between them, and that 0 to 0.4 is kind of the gray area, where it may have nonpolar properties, it may have polar properties. Obviously, the higher it is, the more polar it's going to be. So this is 1.2. It's still a covalent bond, but it's a polar covalent bond. And then let's do, real quick here, let's do this one. We know this is not going to be covalent, but let's show that with this. What's the electronegativity of sodium? 0.93, and chlorine? 3.16. I'm just gonna do it that way. Pretend that I'm subtracting them big from or small from big. What is the answer? Sure, whatever. We'll say it is because it doesn't really matter because look here, greater than 1.7 is ionic. It's an ionic bond. Sure. What I don't know. I'm not gonna ret flag here. It's just we know it's going to be greater than 1.7. If you want to do the math, you can. Peyton's going to be doing that right now. It says. Why does it matter? What is it? What does this have to do with reality? 2.23. Thank you. What does this have to do with reality? Well, there exists such a thing. We're talking here about intramolecular bonds. These, by the way, we also call covalent bonds molecular bonds. I should have said that yesterday, but you probably already knew that. We call covalent bonds molecular bonds. Right here. Hold on. Pause. I said that was a lie. Okay. So we have an ionic bond here. We have a polar bond, and we have a nonpolar bond. In addition to there being bonds that hold atoms together in a molecule or in a formula unit, there are also bonds between different molecules. We call those intermolecular. So if we have a whole mess of water, because why have I drawn it like this? It's what's called a space filling diagram. We just kind of draw the outline of where and we make them touch. But anyway, if I have a whole mess of water, because almost always in chemistry we're not dealing with a single atom, because you can't see it. It's a little baby. So we're usually dealing with a whole mess. And what this means is that the negative end of this one, which I've done it wrong, this is the positive end, is attracted to the negative end of this one. Look, let me rephrase that so that it actually makes sense. The positive end of this one is attracted partially. It's not as strong as the attraction between an electron and a proton, but the partial positive charge of this one is attracted to the partial positive charge of this one, and that causes bonding. This is what gives water the properties of, if you, with my tea is mostly water, this is not going to show up on camera at all, but if I dump a little bit of tea on the table, a tiny bit of tea, and there's a little bubble up, and also you saw it as I was pouring it out, it kind of sticks. That stickiness is because of the bonds between these and between the different other materials. So, thanks, Peyton. So if we dump some water on the table, the reason it all pools up, like if this were a perfect fluid, if this were liquid helium, which behaves as what we call a superfluid, it would have just gone, like it'd be gone. But it piles up because it's attracted, every molecule is attracted to the molecules around it, and every molecule is attracted to the table that's touching the table, and there's some interaction with the air too, and that's because of these intermolecular bonds.
And since you don't have a bond with water, that's why you displace water.
You do bond with water.
Well,
so now look at this one. This is nonpolar. One of the reasons this is a gas is because there's very weak attraction between hydrogen. I'm just going to draw them like this. These are supposed to represent one hydrogen and another hydrogen. This is a hydrogen, a diatomic hydrogen molecule. There's only very weak attraction because there's no partial positive or partial negative end. I shouldn't say that. There's no what we call a permanent dipole. There's no one isn't always positive and the other isn't always negative. Because of the random fluctuations of electrons, there's always going to be some attraction between them, but it's much, much, much weaker. And so instead of being a liquid, the hydrogen is a gas. And that's one of the reasons for this. Do you have questions about, this is a kind of a real crash course in polarity, but do you have questions about this? Last thing, generally, polar compounds can dissolve other polar compounds, and nonpolar dissolve other nonpolar. That's why oil and water don't mix. So water is polar, Oil is nonpolar. If you try to mix them, they don't because one doesn't dissolve the other. We say like dissolves like. They have to be alike to dissolve one another. Polar dissolves polar, nonpolar dissolves nonpolar, and you can't mix them. They don't dissolve each other.
So, what makes water polar and oil not?
Water is polar because there's this bond character difference. There's a difference in the attraction of the electrons to the hydrogens to the oxygens, as we said before. That makes it polar. And then oil is nonpolar because even though, very, very, very roughly, oil we can think of as a very long chain of carbons that are all bonded, and then each of those has a little hydrogen bonded to it too. This is really simplified, and there are different kinds of oil, but generally it's like this. And so even though, and this is another thing I actually meant to say, so I'm glad you brought that up, but even though this bond, it may not be polar, I don't know the exact math, but there is some difference between carbon and hydrogen. But even though this bond is polar, and this one is polar, and this one is polar, altogether there's no net difference in charge. So the electrons all want to spend more time with the carbon, but there's no difference in its shape because they surround it. Does that kind of make sense? So this one ends up being nonpolar because the charge isn't different from this side to this side, for instance, or from this side to this side. So even though each one bond is itself polar, it's surrounded, and so it's not polar. The classic example of that is methane, which is just carbon with 4 hydrogens. Each bond is polar, but this substance is nonpolar because it's shared all the way geometrically around it. Does that kind of make sense? Okay.
The oil that you drew.
Yeah, let's.
Is that like bond length? Like, is that the bond length?
No, bond length is the distance between the hydrogen and the carbon, for instance. And remember, we did talk about that yesterday, but that's just they get closer together the stronger attracted they are. So bond strength and bond length, remember, were inversely proportional, but that doesn't really necessarily have to do with this. I'm sure it does to some extent, but it certainly does when you talk about intermolecular bonds. Like the hydrogen or the water molecules are going to be much closer together because of that exact principle than the hydrogen gas molecules would, which is one of the reasons that the water exists as a liquid at room temperature and hydrogen gas doesn't. Okay, now let's do next covalent naming. This we have very little time, and this should be very fast. For covalent naming, it's usually pretty dang quick. We have a set of prefixes. Mono, bi, tri, tetra. These should be familiar to you from physical science, which is why we can spend very little time and hopefully get it. Hexa, hepta, nona. Oops, sorry, I forgot one. Octa. Octa, nona, deca. You should not have to go higher than octa because of the octet rule. But in case there are nona and deca, which sometimes does happen. Mono, 1, 2, etc. Deca is 10. These prefixes just mean how many there are. So for instance, if we had H2Br. Well, just as a substance, we would call this, let's just, no, I don't like that one. I'm sorry. Let's do a different one. Because this doesn't exist, so let's do one that does exist. We just name the first thing. We name them in order. Carbon disulfide. Di comes from how many there are. So unlike in ionic naming, where we were talking about the oxidation state, now we are talking about how many there are. So carbon, if there isn't a prefix, it's 1. Disulfide. You know this one. You know what this is even before you know this naming scheme. Carbon dioxide. What about this one? Carbon monoxide. And we have to be specific with the mono because, and we usually only use mono when there's another more common thing that has another number. So we can't just call it carbon oxide because these are both carbon oxides. We have to specify this one as carbon monoxide. And that's really it for covalent naming. We use this, I'm sorry, this should be di, you're right. We just use this to represent the number, and then we say their names. And that's covalent naming. It goes back and forth, obviously. If we have the name, we can translate that into numbers. If there isn't one, we call it, it's 1. It's just 1. It's just one. Questions about covalent naming, because that's really it. I mean, that's as deep as it gets for covalent naming. Now, real quick, this is where people do get confused. You have 5 minutes. Let's talk about acid and base naming. Base naming should be really easy, depending on the kind of base we're talking about. If we're talking about the basic Bronsted-Lowry definition of base, it's just anything that has the hydroxide ion, and you already know that. So it's going to be named with ionic rules. I included bases with acids because I wanted to define it. So bases, depending on the definition, there are different definitions, but the most basic definition is, LOL basic, the most basic definition of a base is bases release hydroxide ions in aqueous solution. Bases release hydroxide ions in in aqueous solution. And then on the other hand, acids release hydrogen ions in aqueous solution. Remind me, what does aqueous solution mean? Aqueous solution means dissolved in what do you think the root word of aqueous is? Water, dissolved in water. So these only count as acids or bases when they're dissolved in water. Look at what happens if we combine an acid and a base without worrying about the other bit. What happens if we combine a hydroxide ion and a hydrogen ion? Just add these together, smoosh them together. Cation first, anion. HOH, rewrite that. H2O, it's water. When acids, by this definition, when bases and acids combine, we always get a salt, some metal, combined with an anion, and water. So for instance, if we had a base like sodium hydroxide plus our acid, hydrochloric acid, these both have to be in aqueous solution, we get water and sodium chloride, which is table salt. It's not always sodium chloride, but it's always a salt, a cation and an anion, and an anion.
Would you write H2O? Or would you write H2O?
This is usually how we express it for acid-base chemical reactions. Let's talk about real quick that bases will be very easy to name. It's always going to be MOH, where M is a metal. It might be something like, if it's calcium, it'll be CaOH. But it's still calcium hydroxide. It's always going to be some metal hydroxide by this definition. Acids are a little bit trickier. To name an acid, we have 2 general rules. We have binary acids. What's binary mean? Yeah. And we have oxyacids. So in binary acids, it's always going to be hydro whatever ic acid. And where the binary is whatever element it was. So for instance, if it was HBr, it would be hydrobromic acid.
Oxyacid is hydrogen and oxygen.
Nope, oxyacids are always from oxyanions. So it's always, this one, in oxyacids we change the we change the ate at the end of the oxyacid, or oxyanion. The ate from oxyanion becomes ic, and an ite from the oxyanion becomes us. So if we had CO3, what's CO3? What polyatomic ion is CO3? Sorry, H2CO3. What polyatomic ion is CO3? Carbonate. So now the H from that becomes ic. So now instead of carbonate, it's carbonic acid. So we add acid. So we just take the name of the oxyacid, the name of the oxyanion, and change it, depending on this rule, to a new name and then add acid to the end. So for binary acids where it's just hydrogen and some other monatomic anion, we use this rule. It's always going to say hydro. This one will always say hydro something acid. And for oxyacids, it never says hydro, and it's just the name of the oxyanion changed and then add acid to the end.
Even though
You will need practice. You will need practice. What? Well, you mean like if it was bicarbonate?
An acid contains both hydrogen atom and an oxygen.
Not always. An oxyacid will contain a hydrogen ion and an oxyanion. This had to be really fast. We usually spend quite a bit more time practicing this. Does this kind of make sense? This should be easy. The base naming should be easy, and then the what was the thing we do right? The covalent naming should be very easy. And you have practice with all of this from physical science, so this should be easy. This is where people get kind of tripped up, and then the polarity is new. So make sure you understand the concepts of that. You're 1 minute late. Do you have questions? I said please stop recording.